We are going to need, for this unit, to be able to draw Lewis structures. I'm going to briefly go through this. Remember, there is a video back in Unit 4 on more detailed of drawing Lewis structures. Remember, we're going to be drawing Lewis structures for covalent substances. This is just because this unit, we're going to be using this a little bit more than we have in the past. So remember, we're using the NAS method, which stands for needed, available, shared. We have carbon dioxide here. The first thing we're going to do is we're going to count up how many electrons are needed. So for most atoms, they need 8 electrons. The exceptions to this are hydrogen and helium. Well, and boron. Hydrogen and helium only need 2, and boron needs 6. So we don't have those 3 exceptions. So we have 3 separate things needing 8. So we need 24 electrons. Available stands for how many electrons are here. So each carbon has 4. We have 1 of those. And then each oxygen has 6. So we're going to multiply that by 2. So we end up with 4 plus 12, which gives us 16. So that's how many electrons we have available. So then we subtract needed and available, and we're going to end up with 8 shared electrons. Remember, when we're talking about electrons, we quite often refer to them in pairs. So we have something we call shared pairs of electrons. So we have 8 shared electrons, so we're going to divide that by 2 to give us 4 shared bonds. So this is something to keep in mind when we're drawing our Lewis structure. So when we draw our Lewis structure, we have carbon and oxygen. Carbon is going to be your central atom. Carbon's always the central atom if you have it. You can kind of infer if you have fewer of one of the atoms in your molecule, it's going to be your central atom. So we have carbon, and I just usually draw it kind of symmetrically. So I'm going to put an oxygen on each side. So usually the first step is just drawing your bonds. You need to have one bond to everything. Keep in mind, we don't usually form circles or triangles or any other like connected shape. We don't have that. So we have an oxygen bonded with a carbon, and then a carbon bonded with another oxygen. So right now we have 2 shared pairs of electrons, but we need a total of 4. So what that means is we're going to need to put 2 more shared electrons. So we now have to take a look at how many electrons each thing has. Keep in mind, everything would like to have 8. 8 allows it to achieve maximum stability. So we have carbon and oxygen to start with. So the carbon now has 2, 4, 6, 8 electrons. So the carbon has enough electrons. But both oxygens only have 4 electrons. Right now we only have 8 electrons. We're going to have a total of 16. So we've already used 8 of our total. So we're going to, whatever is left is going to be what we put on the remaining molecule, on the molecule. So we have, we'll take the 16 minus the 8 to give us 8 electrons left. So what will happen, each oxygen is going to get 4 electrons. These are not shared pairs, these are lone pairs. So my carbon has 2 double bonds, and each oxygen has 2 double bonds to the carbon, or has a double bond to the carbon, and 2 shared pairs. So I do want you to try CF4 and H2O on your own. We're going to look at NCl3 here. So we're going to follow the same process. Needed, available, shared. So we have 4 things here that are not exceptions, so they're going to have a total of 4 times 8, which is 24. Available, we have, oh, that's 32, not 24. Available, we have 1 nitrogen, which has 5, plus 7 from each chlorine, which we have 3. So it's going to be 24 plus 5. Actually, it's 21 plus 5. Sorry about that mental math break. So we have 26. So 32 minus 26 is going to give us 6. So that indicates we're going to have 3 shared pairs of electrons, or 3 bonds, in other words. So nitrogen is going to be our central atom, and we know that because we only have one of them. And if you look at the periodic table, you're going to see nitrogen has 5 valence electrons, which indicates it's going to have 1 pair and 3 single electrons. So I'm going to draw my 3 chlorines kind of evenly around the nitrogen and draw my bonds. I have 3 bonds. I know that because 6 divided by 2 is 3. I have those 3 bonds and 3 things to bond it to, so that makes sense. So of my 26 electrons, I've just used 6 of them, so I have 20 remaining. What we have to do is go through and make sure everything has a full octet. Right now, the nitrogen only has 6 electrons. It needs a total of 8. So we're going to put a pair on the top of the nitrogen. That gives nitrogen a full octet. So now I have 18 electrons remaining. Well, 18, I have 3 things that are identical. 18 divided by 3 is 6. So each of the chlorines is going to get 3 lone pairs on it. And I then have my Lewis structure. So again, try the other 2 by yourself. Pause the video. So for the remaining 2, I am showing what my work was. For CF4, I ended up with 8 shared pairs. You should end up with carbon in the center. Each fluorine should have 3 lone pairs and 1 bonding pair for a full octet. And then for H2O, remember hydrogen needs 2 to have a full octet or a full outer orbital. So you need 12. You have 8, so you have 4 shared pairs, so you have 2 bonds. 4 electrons left, so you have 2 pairs on the oxygen, because that's the only place it will go. So again, this was meant to be a quick review of Lewis structures for you, because we are going to be using them. VSEPR is also coming back here, the valence shell electron pair repulsion. So this is used to describe the so VSEPR is used to describe the 3D structure of the molecules. When we're using VSEPR, single, double, and triple bonds act the same. And then unbonded electrons or lone pairs of electrons take up more space, so it affects what you have for your overall shape. Electron densities, so lone pairs and bonds, will arrange themselves equidistant around the atom in order to minimize repulsive forces. So here we have the 5 shapes that we're going to be focusing on. We did take a look at a few more shapes. We're not going to look at those right now. We're just going to focus on these 5 shapes: linear, bent, trigonal, planar, trigonal pyramidal, and tetrahedral. So in order to determine the geometry, we're going to draw the Lewis structure, count up the number of bonds on the central atom, and then use the chart to determine the shape. Keep in mind, you won't have the chart on your test. So we have a few examples here. So the first one, we've kind of already done the Lewis structure for it. So what we're going to do, we kind of can fill in this information from what we've already done. So we said NAS, needed, available, shared. So we need 12. We had 8. So that means 4 are going to be shared. So oxygen was in the central. We have 1 bond on each side to hydrogens. So you have, of your 8 electrons, you just use 4 of them. So you have 4 remaining. And those 4 are going to go on your oxygen. So we kind of just did this one. So went through it kind of quickly. So here's the thing. What we want to do to determine the shape we take a look at the number of shared pairs on the central atom and the number of lone pairs. We sometimes call shared pairs bonding pairs. They're the same thing. In this case, we have 2 bonding pairs, or 2 shared pairs, and 2 lone pairs. So we have 4 total. We take a look at our chart on the previous page. 2 bonding pairs and 2 lone pairs is bent. For right now, we can ignore this IMF. Don't cross it out because that's what we're going to talk about next class. We're going to come back and identify these. But this is going to have your bent shape. And your polarity here is going to be polar. So if you look at your shapes, if something has a lone pair on the central atom, so bent, remember there's 2 bents, or trigonal, planar, it's automatically going to be polar. So those 3 are always polar 100% of the time. We'll need to figure out the other's polarity at another time. So what I'd like you to do, I'd like you to fill in these 6 examples. Again, don't cross out IMF, just leave this for later. We're going to come back to that at a later time. Okay, so you can get started. So taking a look at SCl2, this one's a little bit tricky. You have to go through needed available shared. You have 3 atoms. Each need 8 electrons, which gives you a total of 24. You then, available sulfur has 6, and you have 1 of them. And then chlorine has 7, and you have 2. So 6 plus 14 is 20. You have 4 remaining shared electrons. So when I drew it, I started with sulfur in the middle, and I know this because sulfur, there was only 1, making it most likely for the central atom. And put 1 chlorine on each side. So I had 4 shared electrons, which means 2 bonds. So I had 1 bond to each chlorine. So I subtracted those 4 electrons from my 20, which gave me 16 electrons remaining. I then took a look at my central atom. I needed to get 8 total, and it only had 4 electrons at the moment. So I added 4 more, which made sulfur have a full octet, leaving me 12 electrons. So the 12 electrons remaining, there's 2 atoms left for 12. I divided it in half, and each chlorine got 3 pairs or 6 electrons total, using up all of my electrons. So the common mistakes here would probably be forgetting about sulfur needing some lone pairs of electrons. So it has 2 bonding pairs, 2 lone pairs, making it bent. Because there's these lone pairs on your central atom, it's going to end up being polar. So then my 3-dimensional shape here is drawn very similarly to tetrahedral, because this bent is following the tetrahedral family pattern. So you have your 109-degree angle, and then your one with the triangle coming out towards you, and the one with the dashed line going into the paper. So I actually had a mistake on my 3D structure. You should have your 2 lone pairs here. You only have 2 chlorines, and you usually put the chlorines on the solid lines. The 2 lone pairs remaining, I then put on the one coming out of the paper and one going behind. When you see the molecule, you can't see the lone pairs, so that's why we call it bent for the shape. Sorry about that. Taking a look at chlorine, chlorine is a little bit tricky. You don't really have a central atom, but whenever you have 2 things connected, they're going to be linear. And this is nonpolar because they're going to be sharing the electrons equally. Remember, polarity has to do with how the electrons are being shared. For chlorine, it's equal in this one. So taking a look here, BF3, remember boron's an exception. Boron has a maximum of 6 electrons. So when we calculate our needed, we need that. So you end up with 30. And then you have 24 available electrons, leaving 6 to be shared. Those 6 shared end up being your 3 bonds. After you use up those 6 electrons, you have 18 remaining. If you take 18 divided by 3, you would have 6 on each fluorine. The other one, NH3 or ammonia, similar process. You have 14 needed electrons, you have 8, so you have 6 shared. So I took 8 minus 6 because those 6 were used up in the shared, leaving 2 left. So those 2 are going to be those on the central atom of nitrogen. I know to put it on nitrogen because all the hydrogens can't hold any more electrons.